Hey guys, welcome to Chapter 11. Chapter 11, we're going to talk about intermolecular forces, and we're going to throw phase diagrams in there as well. So intermolecular forces are how molecules are going to interact with one another. So let's just real quick review what we've done so far in this textbook, how we've kind of built up to this point. So the first thing that we talked about were subatomic particles. So we talked about protons, neutrons, and electrons. Then we put those protons, neutrons, and electrons together to form what we call atoms. And then from atoms, we looked at how different atoms interact with one another, mainly their electrons, how they interact with one another to form these things called compounds or molecules. Then we took those compounds and molecules and put them together to see if and how they would form a chemical reaction. So we started with the smallest subatomic particle, we built up to a compound or a molecule, and we looked at chemical reactions. So remember this textbook, structure determines properties. So we looked at the structure first, and then we started talking about some of the properties of those different compounds and molecules. We're going to continue with that theme today. So what we're going to talk about now is something called intermolecular forces. So I've got a beaker full of atoms or molecules or a mixture of the two of them. I'm going to see how those interact or don't interact with one another. Okay. So first scenario that I'm going to pose, and this is something that we're not going to be able to answer right away. It's going to take us a few lectures to get there, but something we can pose now and think about and refer back to. So ethanol and dimethyl ether, these two compounds are known as what we call isomers. So not something you're responsible for, but something I'm going to introduce here. So an isomer means that they're going to have the same atoms, the same made up the same thing, but they're going to be different structures. So everything's going to be connected just a slightly different way. So both ethanol and dimethyl ether are going to have 2 carbons. Both of them are going to have 6 hydrogens, and both of them are going to have 1 oxygen. We're just going to put it all together slightly differently. So same atoms, same molecular mass, different structure. So here we see ethanol. So again, ethanol, we see the 2 carbons, we see the 1 oxygen, and we see the 6 hydrogens. What is something that we know about ethanol? So ethanol is commonly found in your alcoholic beverages. So ethanol is a liquid at room temperature, right? Dimethyl ether. So again, we see the 2 carbons, the 1 oxygen, the 6 hydrogens put together in a slightly different fashion. Here, the oxygen is smack in the middle. Dimethyl ether is a gas at room temperature. So ethers are very often used as anesthetics. So if you think about anesthetics that knock you out for a procedure, it's typically some sort of gas that you're breathing in, right? So this dimethyl ether is a gas at room temperature. Well, if these are the same atoms with the same mass, why is one a liquid at room temperature and the other is a gas at room temperature? Well, its structure determines properties. It's the interactions between these molecules that causes one to be a liquid and one to be a gas. Okay, and we'll talk about the explanation as to why in a few lectures. The first thing I want to review here, though, is the states of matter. So that is one of the properties that we can very easily observe with these different compounds. So let's talk about these states of matter and maybe get an idea of why something might be a liquid or a gas. So the 3 states of matter are solid, liquid, and gas. So just a quick review, solids are packed very closely together, so super, super close. There's a very strong interaction between those particles because they are packed so close together. And these particles can only oscillate and vibrate in place. They cannot move relative to one another. So solids have that definite structure. Liquids, again, still very closely packed together, still pretty strong interactions, not as much as a solid, but still pretty strong interactions. Liquids, however, can slip and slide past one another. So they have a little bit more freedom to move. So they don't have a definite shape, but they do have a definite volume. They take up the volume of their container. And then lastly, gases are very, very far apart. Little to no interaction between those gas molecules. They're free to move about. And they fill up the shape of the entire container. We can compress them a little bit. So indefinite volume, indefinite shape. So thinking about a solid and a liquid. A solid and a liquid have very strong forces between those particles. Because the particles are packed so closely together, we see a very strong interaction with those particles. They also take up a little bit less space. So if we look at a liquid versus a gas, our liquids are a little bit more condensed here, where gases take up a lot more space. Example would be propane. So propane is stored as pressurized. And the reason that it's pressurized is because liquid propane would take up a lot less space than the gas propane. So we see that the gas is a much more condensed amount here. Okay. So what are the things that we need to overcome to go from a solid to a liquid, or a liquid to a gas? Or what's something that needs to happen to go from a gas to a liquid and a liquid to a solid? So what are some of the things that help us transition from one state to the other? Okay. Well, if we think about a solid to a liquid, so if we think about ice melting into a cup of liquid water, okay? So going from ice to liquid, we would certainly want to heat up that sample, right? So we could take the ice out of the freezer. So instead of being at 32 degrees Celsius, we might be at room temperature at 35 degrees Celsius, for example, or 0 degrees Celsius, 0 degrees Celsius to room temperature at like 25 degrees Celsius, okay? So we're going to heat that up, okay? If we want to go the other way, so say we want to go from a liquid to a solid, we would have to cool that down. So if we want to go from liquid at room temperature to a solid, we would have to take heat out of the system, or we'd have to cool that sample down to get our solid ice. Okay. So unfortunately in chemistry, we don't talk about heating it up, cooling it down. We talk about it in terms of energy, right? Kinetic energy. Okay. So our liquid is going to have an average kinetic energy and an average molecular attraction. So it's going to be kind of like the middle child here. Okay, so the kinetic energy of those particles is going to be kind of an average between the two. The attraction is a pretty strong attraction, but certainly could have more, could have less. Solids have a very low kinetic energy, so not a lot of movement in a solid, right? Vibration, oscillation in place, that's about it. So our solids are going to have a very low kinetic energy, but they're going to have a very high molecular attraction. So with those particles being packed so close together, they're going to really like each other because they're so closely packed together. So high molecular attraction. And gases over here are going to have opposite. They're going to have a high kinetic energy, so lots and lots of free motion that they're going to have to bounce around. They're going to have a really low to no molecular attraction. So gas particles being so far apart from one another don't really have to interact, don't really want to interact with one another. So low attraction. Okay. So the state of a substance, a solid, a liquid, or a gas, has a lot to do with the balance between kinetic energy and the attraction between atoms or molecules. So when I was talking about this heat it up, cool it down, that was addressing this kinetic energy piece. So we've talked about that already in the thermodynamics chapter. That's probably something that's fairly intuitive because heating things up and cooling things down is something we do very often. The piece that we're going to focus on today, or in this chapter, is this attraction between atoms and molecules. So what happens if the attraction increases? What happens if the attraction decreases? And what factors go into that increase of attraction between the molecules? Okay. So one misconception that I want to just throw out there really quick and get it out of our heads is this idea of intermolecular versus chemical bond. So chemical bonds are way, 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 way stronger than these intermolecular forces. Intermolecular forces are going to seem really strong because that's all we talk about this chapter. But when we compare a chemical bond versus an intermolecular force, these chemical bonds are exponentially stronger. Okay. One of the ways that we can observe that is the size of them. So chemical bonds tend to be much, much smaller. So shorter bond, stronger bond. These intermolecular forces are not actually bonds. It's really just an attraction. But these intermolecular forces are over a much greater distance. So greater distance equals a weaker interaction. Okay. So chemical bond, short distance, very strong. Intermolecular force, greater distance, a lot weaker. Okay. So just get that out of the way. All right, so chemical bonds are an example of intramolecular. So intra means interactions within a molecule, okay? So intramolecular actions within a molecule are things like ionic bonds, covalent bonds, things we talked about in General Chemistry 1. And those intramolecular forces are very, very strong. Okay. Intermolecular forces, what we're going to be focusing on this chapter, is interactions between molecules. So if I put two water molecules into a beaker, how do they interact with one another? What are the interactions going on between those two molecules? The intermolecular forces that we're going to talk about, and each of these are going to have their own presentation. So we'll come back to these. So the intermolecular forces we're going to talk about are London dispersion, dipole-dipole, hydrogen bonding, and ion dipole. Okay. All of the intermolecular forces have to do with polarity. So all of them, we're going to talk about a charge, right? So polarity is positive is attracted to negative. So when these interactions between molecules happen, it's due to a negative charge somewhere, a positive charge somewhere, and they're attracted to one another. Okay, so electrostatic attraction, that's the fancy word for it. The difference here is going to be the strength of that attraction. So is it a temporary polar moment? Is it a permanent polar moment? How strong is that permanent polar moment? So those are all things that we're going to talk about. This list right here is also a hierarchy list. So London dispersion is going to be our weakest force. And as we move down this list, it's going to get stronger and stronger and stronger. So the interactions or the attraction between the molecules is going to be a stronger and stronger interaction. Okay. So these are the four that we're going to talk about. So this is your introduction to intermolecular forces. So what I'm going to do now is give each of these their own lecture series, their own lecture video, so you can quickly find which one you need. I hope you guys found this helpful.